we're going to need a few facts about fundamental matrices, and I'm worried that over the weekend, this spring activities weekend, you might have forgotten them. So I'll just spend 2 or 3 minutes reviewing the most essential things that we're going to need later in the period. So what we're talking about is, I'll try to color code things so you'll know what they are. First of all, the basic problem is to solve a system of equations, and I'm going to make that a 2-by-2 system, although practically everything I say today will also work for n-by-n systems. Your book tries to do it n-by-n as usual, but I think it's easier to learn 2-by-2 first and generalize rather than to wade through the complications of n-by-n systems. So the problem is to solve it, and the method I used last time was to describe something called a fundamental matrix. A fundamental matrix for the system or for A, whichever you want. Remember what that was? That was something it was a 2-by-2 matrix of functions of t, and whose columns were 2 independent solutions. x1, x2, these were 2 independent solutions. In other words, neither was a constant multiple of the other. Now, I spent a fair amount of time showing you the 2 essential properties that a fundamental matrix had. So we're going to need those today. So let me remind you, the basic properties of X, and the properties by which you could recognize one, if you were given one, is first of all the easy one, that its determinant shall not be 0. Is not 0 for any t, for any value of the variable. That simply expresses the fact that its 2 columns are independent, linearly independent, not a multiple of each other. The other one was more bizarre, so I tried to call a little more attention to it. It was that the matrix satisfies a differential equation of its own, which looks almost the same, except it's a matrix differential equation. It's not column vectors which are solutions, but matrices as a whole which are solutions. In other words, X, if you take that matrix and differentiate every entry, what you get is the same as A multiplied by that matrix you started with. This, remember, expressed the fact, it was just really formal when you analyze what it was, but it expresses the fact that the columns, it says that the columns solve the system. So the first thing says the columns are independent, and the second say that the columns, each column separately, is a solution to the system. That's as far as more or less. Then I went in another direction. We talked about variation of parameters. I'm not going to come back to variation of parameters today. We're going in a different tack. And the tack we're going on is I want to first talk a little more about the fundamental matrix, and then, as I said, we'll talk about an entirely different method of solving the system, one which makes no mention of eigenvalues or eigenvectors, if you can believe that. But first, the one confusing thing about the fundamental matrix is that it is not unique. I've been carefully trying to avoid talking about the fundamental matrix because there is no the fundamental matrix. There is only a fundamental matrix. Why is that? Well, because these 2 columns can be any 2 independent solutions, and there are an infinity of ways of picking independent solutions. That means there are an infinity of possible fundamental matrices. Well, that's disgusting, but can we repair it a little bit? I mean, maybe they're all derivable from each other in some simple way, and that's, of course, what is true. Now, as a prelude to doing that, I'd like to show you what I should have showed you on Friday, but again, I ran out of time. How do you write the general solution to the system? the system I'm talking about is that pink system. Well, of course, the standard naive way of doing it is it's x equals, the general solution is an arbitrary constant times that first solution you found plus C2 times the second, another arbitrary constant times the second solution you found. Okay, now how would you abbreviate that using the fundamental matrix? Well, I did something very similar to this on Friday, except these were called V's. It was part of the variation of parameters method, but I promised not to use those words today, so I just said nothing. Okay, what is the answer? So it is x equals, how do I write this using the fundamental matrix, x1, x2? Simple. It's capital X times the vector whose columns, the vector whose entry, column vector whose entries are C1 and C2. In other words, it is x1, x2 times the column vector C1, C2. Isn't it? Yeah, because if you multiply this, think top row, top row. Top row C1, top row plus top row times C2. That exactly gives you the top row here. And the same way the bottom row here times this vector gives you the bottom row of that. So it's just another way of writing that, but it looks very efficient. Now, sometimes efficiency isn't a good thing. You know, you have to watch out for it. But here it's good. So this is the general solution, written out using a fundamental matrix, and you can't use less symbols than that. There's just no way. Well, but that gives us our answer to what do all fundamental matrices look like. Well, their two columns are solutions. So the answer is they look like X. Now, the first column is an arbitrary solution. How do I write an arbitrary solution? There's the general solution. I make it a particular one by giving a particular value to that column vector of arbitrary constants, like 2, 3, or minus 1 pi, or something like that. So, if the first guy is a solution, and I've just shown you I can write such a solution like x C1 with a column vector, a particular column vector of numbers. This is a solution because the green thing says it is. And side by side, we'll write another one. And now all I have to do is, of course, they're supposed to be independent. We'll worry about that in just a moment. All I have to do is make this look better. Now, I showed you last time, by the laws of matrix multiplication, if the first column is xc1 and the second column is xc2, using matrix multiplication, that's the same as writing it this way. This square matrix times the matrix whose entries are the first column vector and the second column vector. Now, I'm going to call this C. It's a square matrix of constants. It's a 2 by 2 matrix of constants. And so the final way of writing it is x times, it's just what corresponds to that, but x times C. And so this is the most general so x is a given fundamental matrix, this one, that one. So the most general fundamental matrix is then the one you started with and multiply it by an arbitrary square matrix of constants, except you want to be sure that the determinant is not 0. Well, the determinant of this guy won't be 0, so all you have to do is make sure that the determinant of C isn't 0 either. So in other words, the fundamental matrix isn't unique, but once you've found one, all the other ones are found by multiplying it on the right by an arbitrary square matrix of constants, which is non-singular, has determinant not 0, in other words. Well, that was all Friday. That's Friday leaking over into Monday. And now we begin the true Monday. So here's the problem. Once again, we've got our 2 by 2 system, or n by n if you want to be super general. There's our system. What have we got so far by way of solving it? Well, if somebody, your kid, brother, or sister, when you go home says, okay, precocious kid says, okay, so tell me how to solve this thing. I think the only thing you'll be able to say, well, you do this, you take the matrix, and then you calculate something called eigenvalues and eigenvectors. You know what those are? Yeah, I didn't think you did, blah, blah, blah. Well, show how smart I am. And you then explain what the eigenvalues and eigenvectors are, and then you show how to, of those, make up special solutions, and then you take a combination of that. And in other words, it's an algorithm. It's something you do, a process, a method. And when it's all done, you have the general solution. Now, that's fine for calculating particular problems, with definite numbers, a definite model with definite numbers in it where you want a definite answer. And, of course, a lot of your work in engineering and science classes is that kind of work. But the further you get on, well, when you start reading books, for example, or, God forbid, start reading papers in which, people are telling you, they're doing engineering or they're doing science. They don't want a method. What they want is a formula. In other words, the problem is to fill in the blank in the following. You're writing a paper, and you just set up some elaborate model, and A is a matrix derived from that model in some way, represents bacteria doing something or bank accounts doing something, I don't know. And you say, as is well known, the solution is, of course, you've only got letters here, no numbers. This is a general paper. The solution is given by the formula The only trouble is we don't have a formula. All we have is a method. Now, people don't like that. So what I'm going to produce for you this period is a formula. And that formula does not require the calculation of any eigenvalues, eigenvectors, doesn't require any of that. It's therefore a very popular way to fill in, to finish that sentence. Now the question is, where's that formula going to come from? Well, we are, for the moment, clueless. If you're clueless, the place to look always is, do I know anything about this sort of thing? I mean, is there some special case I could solve of this problem I could solve, or that I have solved in the past? And the answer to that is yes. You haven't solved it for a 2-by-2 matrix, but you have solved it for a 1-by-1 matrix. A 1-by-1 matrix also goes by the name of a constant. It's just a thing. It's a number. You're just putting brackets around it doesn't conceal the fact that it's just a number. So let's look at what's the solution for a 1-by-1 matrix. The 1-by-1 case. If we're looking for a general solution for the n-by-n case, it must work for the 1-by-1 case also. That's a good motivation, a good reason for us starting. That looks like x, doesn't it? X inside 1 by 1 case. Well, in that case, I'm trying to solve the system. The system consists of a single equation. That's the way the system looks. How do you solve that? Well, you were born knowing how to solve that, or you, anyway, certainly didn't learn it in this course. Solution is, well, you separate variables, blah, 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 blah. And the solution is x equals, the basic solution is e to the at, and you multiply that by an arbitrary constant. Now, if that's a formula, it's a formula for the solution. And it uses the parameter in the equation. I didn't have to know a special number. I didn't have to put a particular number here to use that. Well, The answer is that the same idea, whatever the answer I give here, it's got to work in this case too. So I'll just, let's take a quick look as to why this works. Of course, you know, you separate variables and use calculus. I'm going to give you a slightly different argument, which has the advantage of generalizing to the n by n case. And the argument goes as follows for that. It uses the definition of the exponential function not as the inverse to the logarithm, which is where the fancy calculus books get it from, nor as the naive high school method, you know, it's e squared means you multiply e by itself, and e cubed means you do it 3 times, and so on, and e to the 1/2 means you do it a half a time or something. So the naive definition of the exponential function. Instead, I'll use the definition of the exponential function that comes from an infinite series. So leaving out the arbitrary constant, which we don't have to bother with, e to the at is the series 1 plus at plus a squared t squared over 2 factorial. I'll put out one more term, and let's call it quits there. If I take this, and then the argument goes, let's just differentiate it. In other words, what's the derivative of e to the at? With respect to t? Well, just differentiating term by term, it's 0 plus the first term is a. The next term is a squared times t. This differentiates to t squared over 2 factorial. And the answer is that this is equal to a times, if you factor out the a, what's left is 1 plus at plus a squared t squared over 2 factorial. In other words, it's simply a e to the at. In other words, by differentiating the series, using the series definition of the exponential, and by differentiating it term by term, I can immediately see that it satisfies this differential equation. What about the arbitrary constant? Well, if you like, you can include it here, but it's easier to observe that by linearity, if e to the at solves the equation, so does a constant times it, because it's linear. The equation is linear. Now, that's the idea that I'm going to use to solve the system in general. What are we going to say? Well, what could we say? The solution to, well, it's better, let's get 2 solutions at once by writing a fundamental matrix. So a fundamental matrix, I don't claim it's the one, a fundamental matrix for the system x prime equals ax. So that's what we're trying to solve. And we're going to get 2 solutions by getting a fundamental matrix for it. Then the answer is e to the at. Isn't that what it should be? That little guy had a little a. Now we've got a matrix. Okay, just put the matrix up there. Now, what on earth is... First person who must have thought of this, it happened about 100 years ago. You know, what meaning should be given to e to a matrix power? Well, clearly, the 2 naive definitions won't work. The only possible meaning you could try for is using the infinite series, but that does work. So this is a definition I'm giving of the exponential matrix. It is. Now notice, the A is a 2 by 2 matrix, multiplying it by t. What I have up here is basically a 2 by 2 matrix. Its entries involve t, but it's a 2 by 2 matrix. Okay, it's going to be, leave out, so we're trying to get the analog of that formula over there. Well, it's going to be, leave the first term out just for the moment. The next term is going to surely be a times t. This is a 2 by 2 matrix, right? What should the next term be? Well, a squared times t squared over 2 factorial. What kind of a guy is that? Well, if A is a 2 by 2 matrix, so is A squared. How about this? This is just a scalar which multiplies every entry of A squared, and therefore this is still a 2 by 2 matrix. That's a 2 by 2 matrix. This is a 2 by 2 matrix. No matter how many times you multiply A by itself, it stays a 2 by 2 matrix. It gets more and more complicated looking, but it's always a 2 by 2 matrix. And now I'm multiplying every entry of that by t cubed, the scalar t cubed over 3 factorial, and continuing on in that way. What I get, therefore, is a sum of 2 by 2 matrices. Well, you can add 2 by 2 matrices to each other. We've never made an infinite series of them, but in fact, we haven't done it, but others have. And this is what they wrote. The only question is, what should we put at the beginning? Over there, I have 1, the number 1, but I, of course, cannot add the number 1 to 2 by 2 matrices. What goes here must be a 2 by 2 matrix, which is the closest thing to 1 I can think of. What should it be? The I. 2 by 2 I. The 2 by 2 identity matrix looks like the natural candidate for what to put there, and in fact, it's the right thing to put there. Okay, now I have a conjecture. You know, purely formally, changing all with a keystroke of the computer, all the little a's have been changed to capital A's, and now all I have to do is wonder if is this going to work. Well, what's the basic thing I have to check to see that it's a fundamental matrix? So the question is this, I wrote it down all right, but is this a fundamental matrix for the system? Well, I have a way of recognizing a fundamental matrix when I see one. The critical thing is that it should satisfy this matrix differential equation. So that's what I should verify. Does this guy that I've written down satisfy that equation? And the answer is, it satisfies. So number 2 is, it satisfies x prime equals ax. In other words, plugging in x equals this e to the at, whose definition I just gave you. If I substitute that in, does it satisfy that matrix differential equation? And the answer is yes. I'm not going to calculate it out because the calculation is absolutely identical to what I did there. The only difference is when I differentiated it term by term, how do you differentiate something like this? Well, you differentiate every term in it, but if you work it out, it's simply, this is a constant matrix, every term of which is multiplied by t squared over 2 factorial. Well, if you differentiate every term, every entry of that constant, of that matrix, what you're going to get is a squared times just the derivative of that part, which is simply t. And the same way. In other words, the formal calculations looks absolutely identical to that. So the answer to this is yes. By the same calculation as before. As for the 1 by 1 case. And now the only other thing to check is that the determinant is not 0. In fact, the determinant is not 0 at one point. That's all you have to check. What's x of 0? What's the determinant at the value of the determinant of x is e to the at? What's the value of this thing at 0? Here's my function. If I plug in t equals 0, what's it equal to? I. What's the determinant of I? 1. It is certainly not 0. So by writing down this infinite series, I've got my 2 solutions. Its columns give me 2 solutions to the original system. There were no eigenvalues, no eigenvectors. I have a formula for the answer. What's the formula? It's e to the at. And, of course, anybody reading the paper is supposed to know what e to the at is. It means that. This is just marvelous. There must be a fly in the ointment somewhere. Only a teeny little fly. The teeny little fly is it's almost impossible to calculate that series. for all reasonable times. However, once in a while it is. So let me give you an example where it is possible to calculate the series and where you get a nice answer. So let's work out an example. By the way, I should, nowadays, we're not back 50 years. The exponential matrix has the same status on, say, a MATLAB or Maple or Mathematica as the ordinary exponential function does. It's just a command you type in. You type in your matrix, and you now say exp of that matrix, and out comes the answer to as many decimal places as you want. It'll be a square matrix with entries, carefully written out. So in that sense, the fact that we can't calculate it shouldn't bother us. There are machines to do the calculations. What we're interested in is it as a theoretical tool. But let's, in order to get any feeling for this at all, we certainly have to do a few calculations. So let's do an easy one. Let's consider the system x prime equals y, y prime equals x. This is very easily done by elimination, but that's forbidden. So first of all, we write it as a matrix. So x prime, it's the system x prime equals 0, 1, 1, 0, x. So here's my A. And so e to the at is going to be, so A is 0, 1, 1, 0. So what we want to calculate is we're going to get both solutions at once by calculating at one fell swoop e to the at. Okay, e to the at equals. Okay, I'm going to actually write out these guys. Well, obviously the hard part, and the part which is normally going to prevent us from calculating this series explicitly, by hand anyway, as I say, the computer can always do it, is the value. How do we raise a matrix to a high power? You just keep multiplying and multiplying and multiplying. That looks like a rather forbidding and unpromising activity. Well, here it's easy. Let's see what happens. What is a, if that's a, what's a squared? I'm going to have to calculate that as part of the series. So that's going to be 0, 1, 1, 0 times 0, 1, 1, 0, which is, da-da. So, brr, 1, brr, 0, 0, brr, 0, 1 plus 0. We are saved. It is the identity. Now, from this point on, we don't have to do any more calculations, but I'll do them anyway, just to, what's a cubed? Don't start from scratch again. God, from 1 times 1, no, 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 no. A cubed is a squared times a, and a squared is in real life the identity. Of course, you would do all this in your head, but I'm being a good boy writing it all out. So this is I, the identity, times a, which is a. I'll do one more. What's a to the fourth? Now, you would be tempted to say a to the fourth is a squared, which is I times I, which is I, but that would be wrong. A to the fourth is a cubed times a, which is a cubed, I've just calculated, is a times a. A cubed I just calculated was a, right? And now that is a squared, which is the identity. It's clear this is, by this argument, it's going to continue in the same way. Each time you add an a on the right-hand side, you're going to keep alternating between the identity a, the next one will be the identity, the next will be a. So the end result is that the first term of the series is simply the identity. The next term of the series is a, but it's multiplied by t. So that is 0. Should I put it, I'll keep the t on the outside. Remember, when you multiply a matrix by a scalar, that means multiply every entry by that scalar. So this is the matrix 0, t, t, 0. I'll do a couple more terms. The next term would be, well, a squared we just calculated is the identity. So that looks like this, except now I multiply every term by t squared over 2 factorial. All right, go for broke. The next one will be this, times t cubed over 3 factorial. And fortunately, I've run out of room. Okay, let's calculate then. Maybe I should do it. Well, no, we're going to need that. Okay, let's do it here. So what's the final answer for e to the at? It is, I have an infinite series of 2 by 2 matrices. Let's look at the term in the upper left-hand corner. It's 1 plus 0 times t plus 1 times t squared over 2 factorial plus 0 times t. It's going to, in other words, be 1 plus t squared over 2 factorial plus the next term. It's not on the board, but I think you can see it's this. And it continues on in the same way. How about the lower left term? Well, that's 0 plus t plus 0 plus t cubed over 3 factorial and so on. So it's t plus t cubed over 3 factorial plus t to the 5th over 5 factorial. And the other terms in the other two corners are just the same as these. This one, for example, is 0 plus t plus 0 plus t cubed over 3 factorial. And the lower one is 1 plus 0 plus t squared, and so on. So it's the same as 1 plus t squared over 2 factorial, and so on. And up here we have t plus t cubed over 3 factorial, and so on. Well, that matrix doesn't look very square, but it is. It's infinitely log physically, but it isn't. It's got one term here, one term here, one term here, one term there. Now, all we have to do is make those terms look a little better. For here, I have to rely on the culture which you may or may not possess. You would know what these series were if only they alternated their signs. If this were a negative, 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 then the top would be cosine t, and this would be sine t. But they don't. So they are the next best thing. They are what? Hyperbolics, right? The top is not cosine t, but cosh t. The bottom is sinh t. And how do we know this? Because you remember. And what if I don't remember? Well, you know now. That's why you come to class. Well, for those of you who don't, and in fact, remember the nice way to, so this is e to the t plus e to the negative t. It should be over 2, but I don't have room to put in the 2. This doesn't mean I will omit it. It just means I will put it in at the end by multiplying every entry in this matrix by 1/2. So if you've forgotten what cosh t is, it's e to the t plus e to the negative t divided by 2, and the similar thing for sinh t. So there is your first explicit exponential matrix calculated according to the definition. And what we have found is the solution to the system, x prime equals y, y prime equals x. A fundamental matrix, in other words, are cosh t and sinh t satisfy both of those, are both solutions to that system. Now, there's one thing people love the exponential matrix in particular for, and that is the ease with which it solves the initial value problem. It's exactly what happens in studying the single system, the single equation, x prime equals ax. But let's do it in general. Let's do it in general. What's the initial value problem? Well, the initial value problem is we start with our old system, But now I want to plug in initial conditions. I want the particular solution which satisfies the initial condition. Let's make it at 0 to avoid complications, to avoid a lot of notation. This is to be some starting value. So this is a constant, certain constant vector. It's to be the value of the solution at 0. And the problem is find what x of t is. Well, if you're using the exponential matrix, it's a joke. It's a joke. Should I derive it or just do it? All right. The general solution, let's derive it, and then I'll put up the final formula in a box so that you'll know it's important. What's the general solution? Well, I did that for you at the beginning of the period. Once you have a fundamental matrix, you get the general solution by multiplying it on the right by an arbitrary constant vector. So the general solution is going to be x equals e to the at. That's my super fundamental matrix, found without eigenvalues and eigenvectors. And this should be multiplied by some unknown constant vector, c. So the only question is, what should the constant vector c be? So we'll plug in, to find c, I'll plug in 0. When t is 0, here I get x of 0. Here I get e to the a times 0 times c. Now what's this? This is the vector of initial conditions. What's e to the a times 0? E to the a times 0. Plug in t equals 0. What do you get? I. Therefore, c is what? C is x0. It's a total joke. It's a total joke, and the solution is, to the initial value problem is, x equals e to the at times x0. It's just what it would have been in one variable. The only difference is that here we're allowed to put the c out front. In other words, if I asked you to put in the initial condition, you'd probably write x equals little x0 times e to the at. And you would be tempted to do the same thing here. X equals vector x0 times e to the at. Now, you can't do that, and if you try to, MATLAB will hiccup and say, illegal operation. What's the illegal operation? Well, x is a column vector. From the system, it's a column vector. That means the initial conditions are also a column vector. You cannot multiply a column vector out front and the square matrix afterwards. You can't. If you want to multiply a matrix by a column vector, it has to come afterwards, so you can do zing, zing. There is no zing. You see, you can't put it in front. It doesn't work. So it must go behind. That's the only place you might get tripped up. And as I say, if you try to type that in using MATLAB, you will immediately get error messages that it's illegal. Can't do that. So anyway, we've got our solution. So there's our system. It's our initial value problem anyway is in pink, and its solution using the exponential matrix is in green. Now, the only problem is we still have to talk a little bit more about calculating this. Now, the principal warning with an exponential matrix is that once you've gotten by the simplest things involving it, the fact that it solves systems, gives you the fundamental matrix for a system, then you start flexing your muscles and say, oh, well, let's see what else we can do with this. For example, the reason exponentials came into being in the first place was because of the exponential law, right? I'll kill anybody who sends me emails saying, hey, what's the exponential law? Okay, the exponential law would say that e to the a plus b is equal to e to the a times e to the b. The law of exponents, in other words. It's the thing which makes the exponential function different from all other functions. It satisfies something like that. Now, first of all, does this make sense? That is, are the symbols compatible? Let's see. This is a 2 by 2 matrix. This is a 2 by 2 matrix, so it does make sense to multiply them, and the answer will be a 2 by 2 matrix. How about here? This is a 2 by 2 matrix. Add this to it. It's still a 2 by 2 matrix. E to a 2 by 2 matrix still comes out to be a 2 by 2 matrix. So both sides are legitimate 2 by 2 matrices. The only question is, are they equal? And the answer is, not in a pig's eye. How could this be? Well, I didn't make up these laws. I just obey them. I wish I had time to do a little calculation to show you that it's not true, but it is true in a certain special cases. It's true in the special case. And this is pretty much if and only if statement. The only case in which it's true is if A and B are not arbitrary square matrices but commute with each other. You see, if you start writing out the series to try to check whether that law is true, you'll get a bunch of terms here, a bunch of terms here, and you'll find that those terms are pairwise equal only if you're allowed to let the matrices commute with each other. In other words, if you can turn AB plus BA into twice AB, then everything will work fine. But if you can't do that, it will not. Now, when do two square matrices commute with each other? The answer is almost never. It's just a lucky accident if they do. But there are three cases of the lucky accident which you should know. So the three cases, I feel justified in calling it the three cases. The three, oh well, I don't know, maybe I shouldn't do that. So the three most significant examples are, example number one, when A is a constant times the identity matrix. In other words, when A is a matrix which looks like this. That matrix commutes with every other square matrix. If that's A, then this law ABB is always true, and you're allowed to use this. Okay, so that's one case. Another case, when A is more general, is when B is equal to negative A. I think you can see that that's going to work, because A times minus A is equal to minus A times A. Yeah, they're both equal to A squared, except with a negative sign in front. And the third case is when B is equal to the inverse of A. Because AA inverse is the same as A inverse A. They're both the identity. Of course, A must have an inverse. Okay, let's suppose it does. Now, of them, this is I think the most important one, because it leads to this law, which is the form in which you shouldn't. That's forbidden, but there's one case of it which is forbidden, which is not forbidden, and that's here. What will it say? Well, that will say that e to the A minus A is equal to e to the A times e to the negative A. So this is true, even though the general law is false. It's because A and negative A commute with each other. But now what does this say? What's e to the 0 matrix? In other words, suppose I take the matrix that's 0 and plug it into the formula for E. What do you get? E to the 0 times T is I. It has to be a 2 by 2 matrix if it's going to be anything. It's the matrix I. So this side is I. This side is the exponential matrix. And what does that show? It shows that the inverse matrix to e to the A is e to the negative A. That's a very useful fact, that the inverse to, this is the main survivor of the exponential law. In general, it's false, but this standard corollary of the exponential law is true, is equal to e to the minus A. just what you would dream and hope would be true. Okay, I've got exactly 2.5 minutes left, which to do the impossible. All right. The question is, how do you, to calculate e to the at, you can use series, but rarely works. It's too hard. You know, there are a few examples, and you'll have some more for homework, but in general it's too hard because it's too hard to calculate the powers of a general matrix A. There's another method which is useful only for matrices which are symmetric, but like that, well, it's more than symmetric. These two have to be the same, but you can handle those, as you'll see from the homework problems, by breaking it up this way and using the exponential law. So this would be 0, B, B, 0. See, these two matrices commute with each other, and therefore I can use the exponential law. This leaves all other cases. And here's the way to handle all other cases. All other cases. In other words, if you can't calculate the series and this trick doesn't work, are done as follows. You start with an arbitrary fundamental matrix, not the exponential matrix. You multiply it by its value at 0. That's a constant matrix, and you take the inverse of that constant matrix. It will have one because, remember, the fundamental matrix never has determinant 0, so you can always take its inverse for any value of t. Now, what property does this have? It's a fundamental matrix. How do I know that? Well, because I found all fundamental matrices for you. Take any one, multiply it by a square matrix on the right-hand side, and you get still a fundamental matrix. And what's its value at 0? Well, it is x of 0 times x of 0 inverse. So its value at 0 is the identity. Now, e to the at has these same two properties. Namely, it's a fundamental matrix, and its value at 0 is the identity. Conclusion, this is e to the at. In other words, and that's the garden variety method of calculating the exponential matrix. If you want to give it explicitly, start with any fundamental matrix calculated, you should forget the expression, using eigenvalues and eigenvectors and putting the solutions into the columns. Evaluate it at 0, take its inverse, multiply the two, and what you end up with has to be the same as the thing calculated with that infinite series. Okay, you'll get lots of practice for homework, and tomorrow.